All right, we're going to dive a little bit deeper in this video into valence bond theory, just to show you how this theory works with expanded octets that involve the d orbitals. And so you have these orbital energy diagrams here. So we saw 2 videos ago that with like carbon, where you have 4 valence electrons, that means you're going to have 2 valence electrons in the 2p, that's higher in energy than the 2s. And there's 2 in the 2s. Okay, so that's a total of 4. You hybridize them and you end up with 4 sp3 orbitals, hybrid orbitals, if you are going to make a geometry that's 109.5 degrees with tetrahedral, right? Then you're going to need sp3s. And so that's kind of ready for bonding, okay? So how is that going to work with like sp3d hybridization? That's Steric number 5. It's the same idea, guys, but you're going to basically excite an electron into the d orbital. So now I have 3s in this case. Remember, this has to be 3rd row or higher. Remember, the expanded octets only can be 3rd row or higher. This is why, because you need to access the d orbitals, at least in the purview of hybrid orbital theory. This is how it all worked, okay? And so then you would hybridize and make these sp3d orbitals that have the trigonal bipyramidal type geometry, 5 of them, okay? If you want to make d2 sp3 hybrid orbitals, like let's say sulfur could do this, again, you need a row 3 or deeper, row 4, row 5 element. And so you're going to excite 2 electrons, again, using sulfur here because this has, 6 valence electrons. So 2 of those are going to get excited to 3D. Then you're going to hybridize, and then you're ready for forming bonds in an octahedral arrangement that have the 90 degrees that you need. You have 6 sp3d2 orbitals. You took 1 s, 3 p's, and 2 d's. So you might be wondering, we went up to Steric number 6. And let me just show you, actually, in my advanced inorganic class I teach to graduate students, we talk about Steric number 7, 8, and I think that's all we do in our class. Yeah, but you can go even higher. Let me show you what some of the 7s look like. Just for fun, you can't really buy models for these because they're kind of weird. They're rare molecules, and you need transition metals. You're going to need d orbitals or f orbitals, and so we build, weird looking models just with toothpicks and marshmallows. I told you could do this, and so this one is called a monocapped octahedron. This is coordination number 7. Obviously, you don't need to know this. This is called a pentagonal bipyramid. You basically have a pentagon and 2 up and down atoms, which make it a bipyramid. And there's some other here. This is called a tri-capped octahedron. And anyway, there's some other ones. So they're super interesting, and it can get kind of complex. You can have multiple different geometries, and we actually go beyond VSEPR. But anyway, you can get up to 15 coordinate. So this professor, Greg Girolami, he was my floor mate when I was in graduate school. He was professor on my floor in the lab that I worked on. Really nice guy. And he wrote a 2-page lab report. Essentially, it was a paper showing the synthesis of a new compound where he set a record for the highest coordination number known. And so this uses thorium and hydrogen type ligands, hydrogen type bonding things to thorium. Thorium is an F block, so it's one of your actinides. So it's a really big atom. And here's a crystal structure. So he was able to figure out the shape of this molecule. So anyway, you can get some crazy high coordination numbers. Obviously, we're not doing that in this course. Just thought it would be cool to share with you that you need to know Steric numbers 2 through 6. Okay, those are by far and away the most common. All right, guys, I'll see you in the next video.